Oh, there we go. Okay, well I would say the video is working in terms of actually recording audio. That's great. And I think if I make something else, oh well, I see what I'm doing. Maybe I can change the resolution correctly. We'll see if that kills the video somehow. I don't think so. No, I think we're good. You can't see anything yet, but now you can. And I need to block out the bottom of the screen. Okay, good. It takes me forever to set up sometimes. Hey, there we go. And I can actually kind of even see the screen on the video there. Perfect. That does the opposite of helping. Okay, well anyway, I can see it on here as it's being recorded. It'll probably look better eventually. Oh, so time to start. Well, good morning, everyone. So welcome to Computer Science 430 yet again. And today we'll be learning about operating systems. And I posted the video of like last class up here. I'm going to start doing that. I had a couple times when the video went wrong, and you know, it happens sometimes. Oh yeah, stuff people found. Let's start with there, because this was amusing. Okay, and I put the kernel versions onto this, and I think I can find this stuff quickly if I highlight that, and then I switch to here, and get this into the right spot, like that. And I think most of these are in 3.2. That doesn't mean you found it in 3.2. I'm just doing this by where I found stuff. And so then, oh yeah, that's already in the right spot. Getting to parent can't be supported generically. The locking is too icky. I thought that was a pretty good explanation of what's wrong with locking there. I like that one. Okay, Argix 86 PCI 448. Notice that in some cases here, it's actually finding it already, because I already went through and found these. And so that's great. Okay, so here's a memory leak. Like, memory leaks are not good, right? You know, that's where it allocates memory and it never says it's done with it. But in this case, it's arguable whether it's worth the trouble to care. So we don't need to worry about this memory leak.
No.
Okay, this one here, recency line something. Oh, and 4.2 source. This is probably not going to work. This is probably going to be different. Is it 42? Oh, well, that's actually pretty funny. Function is complicated by the ultimate brokenness of the IOC3 chip, which is used in SGI systems. So apparently, yeah, that doesn't work too well. Okay, this one. Use FS, whatever, INO.C 2188. Okay. I don't see that. Okay, I'm not sure what's there. We'll just keep going on. Maybe that was the wrong version. Oh, or later. Okay, that's right. It was like somewhere down there. If that ever happens, okay. I think I looked through there and there was something funny, but it says it's a kludge. That's funny, right? Kludge is a funny word. Okay, freezer.c. Oh, this is good. There's all kinds of refrigerator references in this file. I only picked out like one of them, because there's a whole bunch of examples. Refrigerator is a place where frozen processes are stored. Which doesn't seem to make sense to me. It's like, you don't throw frozen stuff in your refrigerator, it would melt. Okay, exit.c, and what was that? 237. I asked you, have you never, okay, so we haven't talked about process control yet. Processes always have a parent, like you have some process that forks into two, and one of them is the child and one is the parent. And so this isn't like human reproduction, it's more like a worm where, you know, they say if you cut a worm in half, both halves go live. I don't know if that's true or not, but that's anyway how processes work. You split it, except it's not how worms work. It's like if you could duplicate the worm. Okay, so you duplicate it, and then the original is the parent, the other one's the child, and if the parent process is done, then the child is orphaned. So anyway, there's a bunch of orphan references in this file, and anyway, usually the parent-child has to take care of stuff when the child process turns into a zombie, but we'll talk about all that later. It'll be fun. Okay, and let's see. Name I. Where was that? 738. What? How's that 738 long? I must have wrote that down wrong. I opened the right line? Yeah. Sorry guys, I think I cut and pasted that wrong or something. Okay, I did check these before. Oh, ASCII art. I didn't go see what it actually is, because I got a lot of escape sequences in there. But I apparently put this into the kernel log. If you're curious about the kernel log, do dmessage, and you get the kernel log. And I see somebody's been sigfolding some 8.0 process, that's fine. And, well, yeah, you know, people just do funny things on a software. I mean, that's just how it works. There's a bunch of stuff for a file system and things, and yeah, it's kernel log message. So there's something that can dump an ASCII art into there, which is awesome. Okay, somebody delved into the assembly code. There's .s file. I don't remember who that was. But anyway, okay. Here in the assembly code, we have this ASCII string, cows can fly. And that's not even a comment. That's like part of the code. And that gets compiled into the kernel. Okay. Okay, drivers. Drivers are always full of good stuff. Okay. Let the user know we don't want to disallow opens for rescue purposes or in case the vendor is just a blithering idiot. Do this after the dev config call has some controls about him. So, yeah, I guess sometimes frustration things happens. And finally, one in here. Maybe a little history on Anonymous after we look at this. Okay. There. I probably had this in the wrong spot. Okay. So MD44 plus like proper present bits in PTEs for Christmas. Cards before I have them, cards after I have them. So, you know, why not? Well, not a good project. So let me see if I can find you a machine, not a software, that has a tainted kernel. So this is the kernel log, and let's go ahead and grep for tainted. No? Oh, taints. Ooh, tainted kernel. Let's get some context. Context, 5 lines. Oh, there we go. Okay. So we got this line in here. This is as it's loading through devices. So you can see here we loaded into mouse. I really like these Microsoft optical mice, and so I have one attached to like all my machines, even though I never use Microsoft products other than their mouse. These opposites on mine sometimes. And so anyway, they make a nice mouse. I like their mouse. I'm not gonna avoid it just because. Okay. So but anyway, so we're loading devices, and here we load the NVIDIA stuff. So. How many people here have something by NVIDIA? Okay, like one. How many people here?
Not my current machine, previous machines.
Okay, so you've had them before. How many people here have had an NVIDIA product they liked in the past? Okay, this is good to most of you. Okay, a couple of you don't like them or don't play games. See, that's the other thing. So here's what the NVIDIA hardware is for. When you're playing a video game, you don't want your CPU calculating everything, because when you go fire a rocket, the rocket has to travel along through the world until it hits your friend on the head. Well, this entire time that it's traveling, its position is going to be updated, and so that changes. The light from the rocket trail is going to reflect off surfaces in the room, and that's going to change. People are moving, you're moving, other things are moving. All this stuff has to be kept up to date, but most of the scene isn't changing. Because, I don't know what you're in, like an old warehouse or an alien cave or something, but, most of it's static, stays the same. And so it would be super inefficient to have this all in main memory, and then it all gets written out to the video card, which displays on your screen. That'd take forever. So what you do instead is you buy this fancy video card. NVIDIA makes GPUs for it. ATI makes GPUs for them. And the video card has memory on it to hold what the world looks like. And then, when your CPU needs to draw something, it tells the video card, okay, the rocket has moved from here to here, this player's moved from here to here, this player's moved from here to here, draw everything. And then the video card updates the locations of those and figures out what the scene looks like in 2 dimensions on your monitor. How fast it can do that is related to your frame rate, because it has to do this often enough that all the motion looks smooth. And that's about 30 times a second. Sometimes gamers say more like 60 is better, and I'm sure that it is because it's a higher number. But anyway, your brain will perceive it as smooth if you're up at 30. So the video card is handling all the drawing. And so if your video game is going really slow, picture like a slideshow instead, you need to send more money to NVIDIA, and then that will fix it. Okay, so that's what NVIDIA does. And but NVIDIA, they're a little secretive about this. I mean, they got their competitors, ATI here, and I don't know if they actually hate each other or not, but I always picture them like disliking each other because they're competitors. Probably actually I'll get together and have parties or something. But anyway, so they're a little secretive about how their card works. And if they revealed how their device driver interacts with their card, it would reveal a lot about how their video card works. And so that's something they don't want to do. So they keep their source code for the video card driver secret, and they give you a compiled version of it. Well, you know, Linux is open source, right? Like the source code is not only open, it's like released under a license where you can have it and all that kind of thing. So this is not really good. So when we put in an NVIDIA driver, it taints the kernel. We moved away from our open source philosophy. We put in an evil binary that was created by a corporation that wants money. Oh, so anyway, that's where the whole taints kernel thing comes from. Okay, so was it this one or okay? Oh, so the Nauvoo folks, they're making this driver, Nauvoo. I don't know how to say it. They picked a name that you can't say. This is not good for marketing. But anyway, it's an open source project to make a driver for the NVIDIA card. So you don't need to use a proprietary driver, and you can keep your kernel pure and untainted. The main problem is the driver team working on Nauvoo, they don't understand NVIDIA's hardware the way NVIDIA does, because like I said, it's a big secret. And so they always have trouble making their driver take good advantage of this hardware they don't know anything about. Well, they know some things about it, but they don't know everything about it. And so typically its performance is like a third of the binary driver. And it can't run all the features of the card usually. Like the card will have stuff where it supports, you know, a whole bunch of screens at different resolutions, or, you know, anti-aliasing, stuff like that. Anyway, their driver oftentimes is behind the times on that. And so they're always frustrated with NVIDIA because they're trying to write stuff for a pick and a poke here. They're like, what does this card do inside? Let's go write a driver for it, you know. I don't envy their task, not in the slightest. Nor do I use their product. But anyway, that's what the whole tainted kernel thing's for. And so that's why there's a number of comments in the source code for Nauvoo talking about, we wish NVIDIA would do this, that, or the other thing.
Is NVIDIA owned by Intel? Or do they have some relationship?
Not particularly. They're their own company. They've occasionally had slight collaborations on one thing or another. NVIDIA's made chipsets for both AMD and Intel processors, and sometimes they're kind of buddy-buddy with Intel on designing stuff. Like they're working on this new NVLink, which is a bus between the card and the CPU. Right now we use PCI Express, and NVIDIA points out that we can get better performance if there's a faster bus here. And so when they do that, their engineers call up Intel, and they're all like, oh, we can make more awesome computers and sell them all. Let's come up with a standard here. So, yeah, I mean, they're friendly, it seems like. I don't know. Corporations having personalities and being friendly with each other is a weird thing to talk about. I mean, it's not really that way. But, yeah, they kind of appear that way. The merger you might be thinking of, AMD and ATI are the same company.
Oh, okay. Yeah, maybe that was it.
Yeah. And so they are unified. And they were kind of the underdogs in this whole thing. So, you know, it's the last alliance of men and elves.
And then you have gamers like me that support them because that's what my machine has.
Yeah. They usually are stuck competing at a lower price point. NVIDIA has the superior technology for the most part to Intel and to ATI and Intel to AMD. And so where they compete is if you got $200 to spend and you want to maximize your frames per second number, then ATI and AMD can be your friend. If you got $5,000 burning a hole in your wallet, you're not going to want their products. But that's not the situation most people face now, is it? Okay. I run NVIDIA stuff because, frankly, their driver for Linux is way better than ATI's driver. Okay, so kernel modules. This is a great lead into kernel modules, actually. So the kernel modules, you know, it's around since Linux 1.2. That's actually after the book that we're going to be studying. And so we're going to use the book to study how the kernel works. In terms of learning how to write for the kernel, we're going to learn how to write for a modern kernel because I think the odds that you're going to be hired at the end of your degree to develop software for Linux 0.11 are slim to none. And so in terms of a useful takeaway skill, I'd like you to know how to write modules for current Linux. And modules, in fact, haven't even been supported in 1.1. So we're going to just kind of cover these separately, and yeah, they won't be in the book. Okay, so the reasons for modules. So here's the alternative. Suppose you want to make a change to the kernel. You want the kernel to have a device in /proc that tells you the time of day when you print out the contents of the pretend file. Now we talked about /proc. It has things in it that look like files, but they're not files. They get some input output from the kernel. Yeah, you got a time of day file in there. Well, one way to do it would be to take your kernel source code and add your modification and recompile it and install it in boot sector of your hard drive and start her up. You got a modified operating system. And that works just fine. I've developed a device driver for NetBSD that way, and I think I did my file system for NetBSD that way too, actually, come to think of it. And it works fine. There's a few disadvantages in terms of writing that way. The practical disadvantage is if you make a mistake when you're modifying the kernel and it doesn't work for some reason, you'll find out when you try and boot up the operating system again because the kernel won't work. And so you better have a backup kernel available. Otherwise, it can be kind of hard to get back into your operating system when you can't boot it. So that's a little irritating. Another thing that's irritating. So suppose you write your modifications to the kernel and you start up the computer and it doesn't crash. That doesn't happen. But there's some mistake, you know. You didn't write it quite right. You need to make some change. So what you have to do to make your change is change the source code for the kernel, recompile it, install it, reboot the computer. And I mean, that's not the worst process in the world. It comes with the risk that maybe it won't boot afterwards, which is irritating. It's especially irritating if the computer is located somewhere that you don't like to work. In fact, the one was when I was doing this. It was in this cramped little room and nobody wanted to be in there. So I was doing this all remotely, and so if you make a mistake, you got to go walk down to the room and reboot the computer. But you know, it just comes with the risk of doing that, and altogether, it's kind of a hassle. For a kernel module, you write your source code in something else. It's not a program per se because you can't run it. It's a kernel object. It's a compiled file that you're going to mash into the kernel. So you write this somewhere else, and then you can put it into the kernel, and you can take it back out. So if you put it in the kernel and it does the wrong thing, you take it back out, and you make the next version of it, recompile it, and put it back in the kernel again without ever rebooting the machine. Now you can make a mistake in your kernel module that crashes the machine, but provided you didn't do that, it's a much faster development cycle, and that's cool. Plus the compilation, the Linux kernel's got a lot of stuff in it. We were playing around with Linux searching and things. We go back to here and we do word count, recursive asterisk C. Doesn't it recursive? Word count everything from find. It ends in it's .c. Okay, there we go. So this is adding up the number of lines in all of them, and ultimately we get this number of lines over here. I'll highlight the thousands part of it. So we're looking at about 11.2 million lines of code here in this directory.
And that's just the C.
Yeah, that's just the C. That's not the assembly. If we put the S in here, oops, back here. There we go. Then we're going to have more than that. Probably not a lot more. There's not that much assembly. 11.6 instead of 11.3. And I didn't include the header files in there. But it can take a while to compile this kind of stuff. Luckily, with a make file, you're not going to have to recompile the entire thing from scratch every time you make a trivial change. You'll have to recompile the file that you're doing, but it's actually going to have to relink a lot of the kernel when it does it. And that's going to take a while because there's a lot of linking to do in that much code. Development of modules, you can compile your module a lot faster. Compiling a full Linux kernel, like start to finish, when I used to do it, it would be like half an hour maybe. These days Harbor's faster. That was in the late 90s, but the kernel's also bigger now, so I'm not sure which way it's actually gone. Anyway, yeah, it takes a long time. That's not good. Okay, reboot less often, yeah, for development. Okay, now in terms of reasons that you would not want modules, one of the common objections to a module is that maybe it's going to be slower. But in fact, it's not actually slower. Once you've mashed a module into the kernel, you're just as fast as if it was written in. The actual mashing in process, that does take a moment. But once it's in there, you know, it's in. It's regular kernel stuff. Okay, and finally, kernel's a little smaller. So you notice in this this kernel source directory. I mean, if we go to what is it? The drivers. Okay, let's go repeat our little how much of the code is in here thing. So we're checking how much of the code is in drivers, and you know, it's not like most of the code or anything. And this is if we had thousands here, it's 6.8 million lines, but it's about half the kernel, and it's just a little over half, isn't it? So that's fairly significant. And most of these are not devices that we have on this computer. I'm not sure I want to do this on this computer. I don't want to make a mess on Nimrod. We'll make a mess on this one. This is the, I have to use here. Okay, this is the configuration tool for the kernel if we were going to go ahead and compile our own kernel. And I used to use this thing regularly. But if you go down here on, say, device drivers and take a look at this, there's a lot of stuff in here where, you know, maybe we have it or maybe we don't. Graphics support, okay. So do we want to have, you know, display panel monitor support? I don't know, probably not on this machine. Do we need an Intel GMA 500 stub driver? Well, I don't have one of those on this machine, so no. You know, you just got a lot of stuff here. Sound card support. Do you want ELSA on here? Okay, you can have it or not. What about PCI devices here? These are all different sound cards. But, you know, I have one sound card in this machine. I don't have all of these things on here. I mean, how many sound cards do you have on your computer? So anyway, I'm just waiting for somebody to chime in and say, well, I've actually got 37 because I like to such and such thing. But because this is a computer science class and people are weird. But anyway, normal people run one sound card. Because like, how many do you need? USB sound device, and here's some of those too. Firewire sound devices, a couple of those. Okay, so for a lot of this stuff, you know, you don't have all of these things in your computer. I don't even have a PCMCIA slot at all in my desktop. This is laptop technology. And so anyway, got all these drivers. And so the question is, do you want them in the kernel or not? And if you don't have kernel modules, you have to decide, do I want my kernel to support this piece of hardware or don't I? And if you say, no, not going in my kernel is going to be small, it's not going to include that device, then if you ever have one and put it in your computer, it's not going to work until you recompile your kernel. And, you know, that can be an issue. So, you know, the other option is, okay, let's just stick them all in here. And then one other place this comes up, so I was talking about that like you're making your own kernel. Well, what if instead of that, you're making a Linux distribution kernel and you're going to go post it and a bunch of people are going to download it and run Linux on their computer? Well, you don't know what sound card they have. So you can include all of them, then it'll work. And that would work, right? Or you can include like none of them and they have to get the distribution and build their own kernel. I guess that would work, but then they have to do that. So it becomes a little bit of an issue. So using modules here, you don't have to stick all this stuff in a kernel. You can make a module. And so ultimately your kernel is likely to be smaller. You could make a kernel that's perfect for your computer and is the same size without modules, but in general people don't build their own kernel, and so modules are going to make it smaller. And you know, I'm talking about the Linux kernel here as an example. Windows kernel is the same way. You know, the driver can either be built into the kernel or it can be a module. Same thing happens on any operating system, really. It's just a generic distinction here. And so when Microsoft's thinking about releasing the next version of Windows, you know, they have to decide, well, you know, what's going to go in a kernel, what's going to be a module. And the answer these days is increasingly it should be a module. Apple doesn't face that same sort of situation in quite as dramatic a manner because they sell their operating system to work on the hardware they provide. And so it might be, well, we haven't put all those sound cards in our machines. We've only used one of those the entire time. Let's just build that one driver in and we're good. And that's a valid thing to say on, when they're doing it, except that sometimes people do like to open up their Macs, which I realize is anti-Apple philosophy to some extent, and change things and, well, and then they run Linux on it. That's just way out of left field.
Well, they fixed that now. You can't even do that now. Even
really?
the desktops and the laptops, it's all just one board and everything's soldered together and glued down.
Oh, there you go. Yeah, they don't need any modules now. Well, except for they have FireWire bus, and so you expect to plug things in and have them work, I guess. They use modules. I mean, every modern operating system uses modules. But yeah. So why not modules? Well, it is a little bit more complicated, having pieces of your kernel that appear and disappear. That's an extra complication. And I put this note, I used to dislike them. Yeah, I used to be an anti-module person. And so when I installed Linux on my computer, I would compile it with the exact drivers I needed for my machine and build it, and I did not have any modules. In fact, I didn't even used to put module support into the kernel. Like, my kernel wouldn't even support modules. Didn't like it. Eventually I got tired of recompiling my kernel all the time. Anyway, so modules are the modern way to go. That's what they're there for. I don't really mean to present this as a discussion of like pro versus against modules. There's advantages and disadvantages, but the community at large has made a decision on this one. And we're going to get dragged into it, so we might as well learn to like them. Okay, stuff that modules are used for. So if there's something that's going to be a core part of the kernel, there's not a whole lot of sense in making it something that can be put in and out of the kernel. I mean, it's just the memory manager. You're not going to take the memory manager out of the kernel, right? And how often do you switch memory managers? Oh, I think I want to try a new memory manager today. You ever wake up and say that? Yeah, me neither. So stuff like that can just get built straight in. There's no reason to have it in a module. Device drivers are pretty much always modules. The reason is, it just doesn't make any sense to compile a device driver into the kernel when you don't even know if you're going to have that hardware or not. And so most of the time these are not. If I was building my own kernel, I might still build in the stuff that's part of the system. It would boot a millisecond faster that way, I guess. But in general, device drivers are going to be modules, especially if you're not building your own kernel. Because if you're downloading something and a kernel that somebody else built, and you're going to run it on your machine, well, they don't even know if you had an Intel versus an AMD processor or what chipset you had or anything. I mean, it's a completely separate set of device drivers, basically. And so yeah, device drivers and modules. File systems. So this might seem a little bit odd if you're coming from a Windows background, because if you're running Windows, you're probably running NTFS. Anybody here running Windows and something other than NTFS? Oh, what are you running?
FAT32.
Okay. It still has some adherence. It's a simpler system, and it's easier to recover your files if everything goes upside down.
Yeah, the downside though is it won't go beyond 4.99 for gigs.
Yeah. Yeah, I mean, that's an issue, but as long as you don't have any files that are larger than that, you want to store it. Yeah, that works. It's got great compatibility with other operating systems too. FAT32 is pretty universal. Okay, but most people in here seem to use NTFS for Windows, and that's what they use. And so you're looking at this like, why don't you just build in NTFS? And Windows may well have it built in. I suspect if we asked Microsoft, they'd tell us, but I didn't do that. Anyway, so then on Linux, there's a wide variety of file systems available. We go to, do we have file system support here? I haven't gone through this menu thing in years. I just use exit device drivers. File systems. Okay, so we can support ext2, ext2, ext4. Apparently that's ext2. RiserFS. JFS, journaling file system. I think IBM put that one together. XFS, that's from Sun Microsystems, I think. I actually used that one on Isoptra. GFS2, I don't actually know anything about that one or that one. So you can see we got different file systems here. Fuse file system and user space. CD-ROM DVD file systems. Well, there's a couple of those. DOS, FAT, you can have FAT32, NTFS. Pseudo file systems, miscellaneous file systems. Oh, we want Apple HFS file system support. So, we're getting to there's quite a number of file systems that are supported on here. Oh, network file systems, NFS. You know, do we want to have our files hosted on a remote machine? I put them on ours. Plan 9. Apparently, Plan 9 was an old operating system that was going to be great back in the 90s. I haven't heard of it in years. I didn't realize we still had support in here for it. So, as you can see, there's a wide variety of file systems that have to be supported here.
What is a pseudo file system?
It's something that looks like a file system, but it's actually not.
Okay.
Pseudo is a generic term for fake or not real or.
But why are those specific ones pseudo? I guess is a better question.
Okay, real file system is one where it's like on the disk, and it's always there. So the first example right in here is the /proc file system, where we got things that look like files, but they're actually it requests the kernel to give you some output.
Oh, okay.
So that and /dev are the big ones. On dev, I don't think you can configure that out of the kernel. But TMPFS, you can have a virtual memory file system for, there's something or other, I've never used it. And I don't really know what huge TLV is either. But yeah, so that's what the pseudo ones are. Yeah, go to FS here and look, there's another way to see all this stuff other than inside the configuration tool. But anyway, so we were going through file systems, and I wasn't bothering to count here, but I don't know, we were at what, 10, 20 file systems, something like that. And it's nice if you support these things, because then if your friend says, oh here, I brought you the hard drive from my Mac laptop because I dropped it in the lake the other day and it doesn't run anymore, but maybe the hard drive's still good. Can you plug it into your machine? When you plug it in, it's nice if your kernel can load a module and go look at the files on his drive, so you can copy them all off. Or tell him definitively that this drive is done for you, You plug it in and it spins up and water squishes out the breather hole. But anyway, so that's one reason that modules get used. Typically, the file systems, it might be that you compile the one you use on your hard drive into the kernel, but the rest of them you just make them modules. And that way, if you haven't loaded a CD that day, when you boot it up, it doesn't actually have to load the CD file system driver into the kernel. I hardly ever use CDs. I use them to load the operating system, and that's like it. And so the CD file system support might as well be sitting in a module in a hard drive instead of as part of the kernel, taking up memory. Oh, haven't got here yet. The kernel can't be taken out of memory. At least it couldn't for a long time. They've been talking about making it able to be taken out of memory, but it's not a standard feature. So if you stick something extra into it, it's in memory. Okay, I guess but unless if it's a module, you can unload the module. Okay, you can add system calls. There's about 100 and something system calls in Linux, and system calls, stuff like read or whatever. You can add one if you want to. It's rare to add one. There's a IOCTL system call. It's used to control devices. So usually, if you are taking some new piece of hardware, you just soldered it together, you're going to stick it in your computer and write a driver for it, you'll use the IOCDL system call to pass information into your driver, which is a kernel module, on what it should do with its device, instead of adding system calls. But you can add a system call if you want to, and then you got your very own function, just like IOCTL, that calls into the kernel. It's rare to do that, but you can, keep it in mind. Network drivers. So there's a lot of network protocols out there. A few of you are veterans of the CS435 class, and so we talked about a whole bunch of protocols, and we talked about how there are a lot of protocols that are obsolete. If you didn't take the class, just there's a lot of networking protocols that aren't used very much anymore. But if you ever ran into them, it would be nice if your computer could play ball. If somebody's like, oh, look at this, I just found a token ring network card, and it fits into PCI slots, I'm going to put it in my computer. It's cool if you have a file system driver to handle the token ring network, network driver. And so you'll have ones that are pretty common, like TCP and Internet Protocol, IP. We're all using those things all the time, and so those could be built in or not. But if you want your computer to know what to do if it has to deal with Apple Talk or something, that's great. The other circumstance here, wireless 802.11 is actually a different protocol than Ethernet. And so it's good if your computer can load a card and talk over 802.11 if it's a laptop. But if you're not using the wireless that day, it might as well not stuff it in the kernel. And if you've got a desktop, you might as well not stuff it into kernel because you probably don't have a wireless card. But if you put one in, it's nice if it works, right? So
That's how my computer runs the internet.
yeah, yeah. So that's a good thing to run as a kernel module. By network driver, I don't mean a network card driver. If you bring home your brand new 802.11 card and you decide to go stick it in your desktop computer, it's going to have to load a device driver to talk to the card. But then it's going to have to load another module, the network driver, that understands how to talk over 802.11. And so what will happen is when you want to send some request, your request will get sent to TCP, which may or may not be compiled into the kernel as transmission control protocol, and then it'll get passed on to Internet Protocol, which might actually be in the kernel, and then after that it gets passed on to the 802.11 system, which gets it ready to go across the Wi-Fi, and then after that it goes to the network card driver, which is the actual, let's turn power on and off to our antenna in the right order, and goes across, and then it's got to go back up the whole series of stuff when it hits your router. And so your router, if it's, probably runs Linux and it's running through the same stack the other direction. Maybe not the same network driver. Okay, and then finally, executable interpreters. So normally we run ELF binaries. Stands for like extendable linking format or something. Let's go to bin. Okay, if we do ls here, we got a lot of programs in our system. So, if I type which ls, this is where it is, the list files program. We do file ls, that tells us what kind of file the program ls is. And it says it's an ELF 64-bit LSB executable and such and such. Okay, that's a format for executable files. The projector has cut off the S's again. I hit auto adjust earlier, but maybe I'll do it again real quick. I don't know why it's suddenly important. I didn't fix it. Yeah, whatever. Okay, so the ELF format. That's one way to put together a binary, but there's others. Remember that when you compile a program, you're compiling machine code for the CPU, but the operating system is responsible for getting the whole thing up and going and loaded into the CPU, and doing system calls and all that kind of stuff. So there actually is a format to it, especially in the beginning of the file, that the operating system has to deal with. And that's where you get to ELF binaries. You can have different formats than that, and they can actually be put in kernel modules. So if you wanted to put in a module that would deal with, I don't know, you want to be famous? Do one for Windows executables. Problem with Windows executables is they got a lot of system calls that Linux doesn't have, and so it's difficult to just plain run them. And vice versa. Applies the other way. That's where virtual machines come in. Okay, so that's what they can be used for. Utilities manage this stuff. So insmod, inserts modules. Insmod, you need to give it a module to insert. I'll show you how to use that one when I show you an example of a module. rmmod does exactly the opposite. It takes it out of the kernel. rmmod sounds like it's going to get rid of it. Like, I'm not going to rmmod it. I just want to take it out of the kernel so I can fix it, and then I'm going to put it back. It doesn't do that. It just takes it out of the kernel. It's safe. You can use it. It won't get rid of it. It'll just get it out of the kernel for you. They probably do this because, in computer science, okay, anybody here watch Star Trek Voyager? Okay, like, what, 2 people? So you guys are supposed to be nerds. What's going on here?
Not that nerdy.
Okay, well, they have a holographic doctor, and so the doctor is a computer program, and they can make him appear in the sick bay, and he fixes people, because they have holograms that do that. Well, the plot of a number of episodes is that they take the doctor and load him onto a portable device that they proceed to lose somehow. And my question is always, why don't they copy the doctor? He's a computer program. They have a portable device that can store him. He can be stored in the ship's computers, obviously, so make a copy. But they don't do that. They put him in a portable device and lose him. They do the same thing with a transporter, but anyway, with regular people. But okay, that all aside. So in the computers, you make copies of things. So probably the reason it's named rmmod is it does get rid of the copy that's in memory in the kernel, but it doesn't go like hunt down your source code for your module and destroy it. That'd be just mean. So anyway, it's safe to run. Okay, depmod tells you what modules depend on. Depmod. Okay, let's give it an actual module. LSmod lists are modules. So that's depmod ATA. That's one of them. Okay, we have to actually go to where it is apparently. Most of these things live in someplace I actually put down here. Live modules. Okay. Live modules. What's in here? Oh, we gotta get the right version. Okay, now, kernel, maybe. Okay. I'm going for something else now,
Okay.
obviously. Okay. Let's see what okay. Well, there weren't any dependency problems, so that wasn't very exciting. This is permission denied errors, because I was trying to run it as a regular user. Well, what DevMod does is it checks to see if there's any dependencies for your module that are missing. And there's probably a way to make it print them out anyway, even if they're actually there. Oh, here. Okay, there's no problems. Okay, here's a list of dependencies and aliases and such. I'm having trouble getting a good output for that. I don't want to spend too much time on it because I'm starting to run out of time. Basically, it helps analyze dependencies for you. K-sims tells you K kernel symbols. And I'm installing here. Okay, I'm not going to install it right now. It'll get more important later, because we'll talk about kernel symbols and versioning and all that kind of stuff at some point. LSMod is probably the main one that you might have used. LSMod. This lists the modules that are currently in your kernel. So here on Isoptera, you see we got modules for all kinds of stuff. XFS module used by something. Oh, there. This one is apparently using XFS. And you can see whether or not modules are actually being used right now by something or other. And if they're not being used for anything, we could probably take them out. I'm a little reluctant to go start pulling modules out of my Isoptera's kernel because it was likely that we're going to cause some kind of problem. But let's back out to this machine here. And so we got all of these modules in here. FGLRX is our video driver. I don't really want to pull that one out particularly. I was debating pulling out the USB stuff, but if we do that, we're going to lose the ability to control a computer because the mouse and keyboard are both USB. The sound stuff might be benign. Oh, Bluetooth. That's pretty benign. We could pull that out. Let's see. It's not going to want to go because it's got some stuff using it. Well, let's take a look at the next one, or the next two. So mod info gives you information. And so here's information on a Bluetooth kernel module. And you can even see who you should email if it doesn't work, apparently. And so that's great. The last one here, modprobe. So what modprobe does is put in and out modules that are installed on the system. And so if we say modprobe-r, that means remove, Bluetooth, probably going to tell us it's in use, even if we sudo it. I'll learn. I'm going to become root anyway. This is something I don't necessarily teach people in the Linux class because they don't get to do it. I mean, I'll tell them sometimes. They don't get to practice. When you want to be an administrator, sudo lets you run a single command as the administrator. And I'll show you the comic on it. Okay.
Is that the
This
bad
is what sudo does. Okay, so on here, if you want to run like one command as user is the administrator, you just do sudo and then you do your command, sudo ls. Hey there, you listed the files as administrator. Look at that. It'll ask you for your password, but it'll remember the password for like 5 minutes or something. So if you're running a bunch of commands in a row, you don't have to type the password a bunch of times in a row. And it's just your user password. So like on these systems, it's learn. Okay, if you do SU stands for switch user, and if you don't tell it who you want to switch to it assumes you want to switch to the administrator. Well, if you just run regular SU, it's going to ask you for the administrator's password. And you probably don't have that. Half the time I forget it on my machines. But if you're an administrator already, like you ran the command under sudo, then it switches to administrator, but it runs the command as administrator, so you don't have to type your password, or type the administrator's password, just your password. You only get to do this if you're in a sudo urge file. Sudo urge. And apparently you have to be administrator to look at that file. See that? See what I did? Put sudo in front of it, so now I printed out the file as administrator. And you can see that that Seth here is given permission to do that, and people in the admin group, and yeah. But I think on all the ones around the room, student is allowed to do it, and so you know, you can change stuff on the machines in this room. You can be administrator anytime you like. Okay, so you just do that, and then you know, type learn if you're on one of these machines. If you're on your own machine, and I don't know your password. Okay, so we're administrator now. Remove Bluetooth. Well, it's going to tell us it's in use. If we look at the modules in here, let's pull one out that's not being used. What file system are we using in here? Okay, we are using, this doesn't tell us. We are using ext4, it looks like. ext4 blocks the pseudo file system, so sysfs. And let's see, dev, yeah, it's running other stuff. We had some stuff running in tmpfs. But I don't see any place in here we're using a B-tree file system. So the question here then is, so why did the B-tree-fs file system driver get mashed into the kernel? It's in that list somewhere. Yeah, it's right there. So let's go ahead and remove it. Okay. Still there? Nope. Gone. And as a matter of fact, these things, XOR RAID 6_PQ and leave CRC32, I mean, they're still probably there. They didn't come up in my little search here because BTRFS is no longer using them. So let's go search for one of those. Hey, they came out of the kernel because they're not being used anymore. So now we're using less stuff. Hey, this is great. We're trimming this stuff down. LP here. That's probably the parallel port. You can't see the L. I'm sorry about that. There's an L right there. That's probably the parallel port driver. Let's try this. Okay. So we got 57 things in the kernel right now. There we go. Now we got 56. Okay. Is there any network driver in here? The Bluetooth thing, but if I want to get the Bluetooth thing out, I'm going to have to go hunt down everything that uses it and that it's using. That's mod Bluetooth. Okay, that's the other way around. I don't know what all. Oh well, actually, if we got BNet and RFCOM out of here, we might be fine. Oh, I won't hunt that thing down. I kind of want to make this machine like stop working somehow. And so I was looking for something that has to do with the Ethernet. I'm a little bit worried that they compiled the Ethernet stuff directly into the kernel, which means we can't take it back out. Because it would make a certain amount of sense to. I mean, how often do you want the network driver to be removed from your computer? I don't want to take the sound stuff out because I'll probably interrupt the video recording if I do that. And I pull out the SATA stuff. All kinds of chaos is going to break these. Enforce 2. This is an NVIDIA chipset, apparently. Okay, we'll pull something out that kills something at the end of the lecture. Okay, promise you a broken computer by the end. Okay, so inserting modules. You can use insmod or you can use modprobe. You use modprobe if it's something that's installed in the system. If it's something you just wrote, you probably use insmod. And just go ahead and insert it. Okay. So let's see. We already pulled some stuff out, which was great. So modules here, when you put them in, they have symbols in it that they look for. Stuff where in the kernel, the kernel is going to have to interact with this module. And the way you do it, your module presents some functions that the kernel is actually going to call, but the module has to be able to see stuff from inside the kernel because it's got to be able to see the inner workings of the kernel. And so since it's got to look at the inner workings of the kernel, there's certain symbols they're called, basically memory addresses. A lot of times when we talk about something in computer science, we give it some fancy term, it boils down to being a memory address. So anyway, we got these symbols, which are places that certain things are, and they'll be exported so that our modules can see them. And let's take a look at proc_kl_sims here. So I recognize this is coming from the proc file system. Okay, see all the 64-bit addresses here on the side? A bunch of Fs and then some more hex. These are all symbols that are available in the kernel for the module to use. And a lot of these are going to be functions that can be called that are part of the kernel. So, you know, like disk flush. That's going to be a function somewhere that you can actually call from your module. So that's how the module can get its bearings. There's this table of stuff, and is available to you when you're writing the module. Okay, use count. I already kind of showed you that when we were unloading stuff. So the symbols here, you know, stuff can be using them or not using them. And I believe this is a user of that symbol. And so if your module adds something to this list and then something is using that symbol, then the thing is said to be using your module. And then the module removal tools won't allow you to just pull it out and leave the other one hanging. Because if you do that, then whenever the other one tries to use whatever symbol that you'd exported before, it's probably not going to work. Okay, so there's a symbol list there. We'll get to that later when we get to programming stuff. But for now, you know, symbols are available. Let's say your module can figure out what's going on. Okay, sometimes descriptive error messages are lacking. A lot of times when something is wrong, your module will give you a could not find kernel version error. That's about the first thing it looks for. And so if something is about to go dramatically wrong, sometimes that's the first thing that goes wrong. And then you'll get this error, when actually what it means is your module is messed up somehow. So you got to keep that in mind with could not find kernel version if you see it. And as usual with programming, descriptive error messages are not always common. Okay, letting you know if something worked. Well, it depends on what it was supposed to do. I mean, if you make a module and it's supposed to sit in the kernel and log keystrokes, and once a month it's supposed to write them into a file, you may have to wait a month to see if the silly thing is working. So you can look at LSMod and see if it's in the kernel, and so you can assume if it's in the kernel it started working. But really, it's kind of up to you to have your module make some kind of effect that you can see. And so when you're writing and debugging it, you might want it to write stuff into the kernel log, or you might want it to make a file in /proc that you can go look at to see what is going on with your module. And that kind of thing is great for debugging. And then once it actually works, don't waste time on it or fill up the log or anything. Well, sometimes when people write this stuff, they end up with like a debug option and then a regular option. And when you're compiling it, like you type make debug or something, and it makes a debug version. So you know, that's how it works with debugging, basically. Unless it does something, you're not really going to know if it's working. Okay, automatically loading modules. You probably don't really want this for if you're writing your own. You want to just like put it in and take it back out. But remember, when you boot up one of these machines, you don't really type in a list of modules you want to have in there. The kernel goes and finds them and loads them. And that's just a standard way to have stuff work. Now there's this auto-clean idea, and this hasn't taken off. When you put modules into the kernel, if you took them back out, then you'd save some memory. And so somebody had this idea, well, when you boot up your machine and you start putting in modules, you're going to end up starting to use up more and more space, you know? And so what if after 6 months, all your friends have come and plugged in various gadgets to your computers and it's got 100 modules loaded that you're not using anymore? It'd be kind of cool if those went away, right? And so the idea of this auto-clean is after a module hasn't been used for some long period of time, like a minute, then it gets unloaded. A minute's probably too fast. But hasn't really caught on. Usually they just kind of build up modules as you go. You don't build up that many, and they're not that big. And how often do you really plug another gadget into your computer? But for some reason, this computer had the B-tree file system module loaded. I don't know why. It didn't seem to hurt anything to take it out. Okay, so yeah, automatic loading is out there, and normally people don't have the modules come back out automatically because then they're just going to have to keep getting mashed in and out for various reasons. Okay, and finally, where are they? So they're in libmodules. And so if we go over here, dp/lib/modules, then you're going to have different versions here for different ones. And you can see these are just minor revisions. So this says run in an Ubuntu distribution here. Ubuntu is infamous for not really being like fully put together and stable when it's released. And so then you have incremental versions that fix stuff. And so this computer here has 8 previous kernel versions worth of modules sitting around in here. And we could probably delete them and not cause any harm. But anyway, so the current ones that are on here are probably the last version right here. If you ever want to see what's running, uname-a. And this gives you all information on the currently running kernel. And so the current kernel that's running is 3130-52. And so that's the last one. It'll usually be the latest one. But if you wanted to check, that's how you check. And so then the modules for this thing are, I gotta actually go like that, are all in here. And if you go to kernel and, let's go to drivers. Should be a lot of modules in here, right? Yeah, there are. Firewire, okay. Is Firewire taken off? I don't know. There's only a few modules relating to it. Those are the actual Firewire drivers, like not for the devices you plug in or for the, the interface itself. Anyway, so that's where our modules live. They just spawn in the file system. Okay, we're not going to get to my demo today. Okay, so as far as versions go, the kernel version has to match. We talked about that before because memory layout might change. If you're doing insmod and you want to put in a module anyway, you can insmod-f and that forces it, just puts it in, ignores versioning differences. And that doesn't change that much from one to the next. And if you look at this one here, this computer, we got all the different ones there that I showed you a moment ago. Different kernel versions that have been on here, and these are not very different. I mean, the odds are if your module worked for 3.13.0-46, it'll probably work for 3.13.0-49. I mean, how much difference are they really going to make without even incrementing the smallest version number here, just 3 vision number? They probably fixed a couple of bugs. And so you can just say insmod-f and put it in instead of recompiling it if you want to. It's better to just recompile it if that's not too hard. But it can be irritating if you're like, oh, I forgot. I wrote my own driver for the wireless card in my laptop because, I don't know, maybe you did. And then I loaded a different revision of the kernel, and now I'm sitting here wanting to get on a network. You might not want to recompile your driver. You might just want to insmod-f it, and that's fine. Okay, symbol versioning. So this isn't always done. One way that a more detailed test could be performed. So here's the basic problem here. You got some kernel running, you got some module, and you got to know somehow if this module can be put into this kernel. And I keep talking about this like there's a person that actually knows what's going on here. Remember, for most computers, this is not the case. Somebody's bought the computer and they got it at Office Depot or somewhere, and they brought it home and they started it up and had all this spyware and AOL free trials on it, and they never deleted it. This is the state of most computers. And so then, when they go back to Office Depot and they get some kind of gadget and they bring it home and they plug it into their computer and they put the CD in the drive that came with the gadget, it's not necessarily going to be great to tell them, okay, well, this driver was compiled for a kernel version such and such, and you have this other kernel version. You should take the driver source code and recompile it for your current running kernel. That's not what they expect, right? So trying to handle this whole thing automatically is kind of required for the modern user experience on computers. And so one way to do that, I just showed you the giant list of symbols. Well, you can have a version on every single symbol, and then you can merge things in correctly. This idea has been beaten around for a while, and I think Linux actually has support for it. I don't think it's really caught on. The reason is there's a lot of symbols there, and they would have to have a lot of versions. And the versioning gets more complicated still when you include the compiler in the mix, because when you're building something with a different version of the compiler, it might just decide to do something slightly different. And so then you got to worry about, okay, we got this version of the symbol, and this module was built with this version of the compiler, and do these things match? Like, can we put this into the kernel, or is it going to cause a problem? So the standard on Linux right now is you got to match the right version of GCC and the right version of the kernel. For other operating systems, Windows, they try to avoid changing anything that would make the drivers that have been running around on CDs obsolete. And this is one reason why the internet is a great thing here, because think about Windows 98 for a minute. How many people here ran Windows 98? I ran Windows 98. About half, okay. I've been using computers a while. Okay, when you got Windows 98, you would have a CD, and the CD, or you might have been able to get it on a stack of floppies. Normally you'd have a CD by then. And so you got a CD, and you put it in your computer, and you load Windows 98. And once you've loaded Windows 98, you go get the driver CDs for all of your hardware, and you put each of those in the computer and load in all the drivers. It was good fun. And so what you weren't doing here is running Windows Update and then downloading the latest version of the driver. It's a lot easier to make things work together that way. Because if you're going to go get a Windows Hardware Quality Lab certified driver, and you're going to put it onto the most recent version of Windows as established by Windows Update, then the versions are both known. And making them work together is a piece of cake. With Windows 98, the operating system just puts the driver in. And it's not like there's a whole bunch of kernel versions floating around for 98. And this was before the Windows Update days. And so you had your version of your operating system, and that was there, and you had your driver, and if it matched Windows 98, that was good enough. And if I recall, Windows 98 was infamous for presenting a certain color on the screen. It had a name. So, and the reason was driver crashes. So you put in your driver off the CD and something would go wrong. Yeah.
Talking about the blue screen of death?
Yep. Yeah.
It's still around, just doesn't pop up as frequently.
Yeah. Well, a lot of why it doesn't pop up as frequently is they've revised this whole matching business here. And so if you're going to go get your driver online and you're going to put it into the Windows Update established latest kernel, there's not so much trouble with compatibility here. Plus, if there's a bug, there's an easy mechanism to fix it. So anyway, managing these things. On Windows, there's a lot less versions of stuff, and so this whole thing is a lot easier. Microsoft Visual Studio is usually used to build stuff in the Microsoft world, and it has major revisions, like 2008 or 2010. It's not like GCC, where you need like 4.6 point whatever. And the same kind of thing happens with the kernel. Like, a kernel change is rare. And so the entire matching pickle here becomes easier. And then the final simplification on it, of course, is people are going to be running the latest kernel. And they're probably not going to take the driver out and put it in on the CD. They're just going to get the one that, hopefully it's already in there sitting around as a kernel module and not put anything in. That's the best. But if not, they're probably still going to be downloading it or something. They'll have the CD, and what you do is you put it in your computer, and it has a program on it that goes and downloads the right driver and installs it. And so the blue screen of death, like I said, yeah, less frequent. It's going away.
Yeah, though there is one easy way to get it whenever you want.
Oh.
Want to know how that is? Bad sector of memory on your RAM stick.
Oh.
If it accesses it, boom, crash.
Yeah. Yeah, there's nothing they can do about that one, really.
Nope.
Yeah.
There's an easier way to get it. You have a TI from NVIDIA, which stands for titanium. It means you can overclock it. They do universal updates for all their graphics cards, and it doesn't always work for a TI. So the last patch, if you download it and then you try and open up Firefox, blue screen of death.
Yeah. Yeah, because they got the kernel the driver has a problem for that particular video card, and when Firefox decides to access that feature of the video card, send it the right IOCTL, doesn't work great. Yeah, so you still have video driver crashes occasionally, and but that's the whole matching pickle. So it's getting better, The other way to get a blue screen of death is to change your friend's screensaver to one that presents a blue screen of death. Like after inactivity. Okay, so yeah, okay. And multiple kernels. Yeah, people do that sometimes. This machine here may still have 8 kernels installed on it. It still has modules for 8 kernels. I don't know if the actual kernels are on here or not. Good chance. You can do that. You just have to have a separate set of modules for all the different kernels. And yeah, that's a hassle. In fact, whenever I update my kernel on my computer, which is not very often, Debian doesn't present that many kernel updates, my video stops working because my NVIDIA module is, there's an interface module that you have to recompile, and it interfaces with their binary driver. Anyway, it'll be for the wrong version, so it won't go into the kernel. And I could force it in, but that's usually a bad idea. So you recompile the interface module, and then everything works again. But that would mean if I switched back and was like, okay, I'm going to boot the old kernel, I'd have to recompile my video card interface, which might be irritating. But how often do you do that again? Okay, symbol licensing errors, yeah, it can happen. Tainted kernel, yeah, okay. Viral GPL, that's another day. Okay, so we'll get on to actually writing one later. I'll just talk about this theoretical scenario here. So theoretically, suppose you decided, I like modules so much, everything is going to be a module. Every single device driver is going to be a module. Every single one. It may actually be possible to boot. This is not the way things are normally done. Here's the problem. If everything is a module, then you're going to have trouble accessing the file system. Because if you can't read the file system, then you're not going to be able to load the modules, which are stored in the file system. I mean, I showed you where they are in the file system, right? So that actually presents a little bit of a chicken and egg problem that makes it hard to boot from the without a device driver. To some extent, you can actually lean on the bootloader. The bootloader puts the kernel into memory. The kernel doesn't have to do that itself. And so if you can have the bootloader somehow hand you your file system driver, then you could go load the rest of the modules. But in general, that's the stopping point in terms of what all can you do. Yeah, loader can load stuff into RAM for you. But yeah, you still have to understand the file system. So there is kind of a limit to this because the kernel has to access the file system to get the modules. But about everything other than that can be put into modules. You know, network card, video card, sound card, all that stuff, that can be in modules. Yeah, I mean, if it can get to its modules, then it can assemble itself. The entire boot up process is called bootstrapping. And it's a reference to picking yourself up by your bootstraps. As you just reach down and grab your shoelaces and lift yourself up. Doesn't work in real life. But it's kind of what the kernel does. Because you start running a piece of the kernel that loads the rest of it. And so it just kind of keeps putting itself into memory. I don't know how many people in here are into machining. I think it would be a fun hobby, but I lack a metal lathe. So I was reading about how to make one using itself. See, what a metal lathe does, spins something around. And so you have a tool holder that holds some tool, and so you can make it a particular shape. Well, a lot of the parts on the metal lathe happen to be round. And of course, if you're making a metal lathe, then once you've made it, you can make round parts for it. So there's a number of procedures that have been worked out where you make some kind of like really primitive version of your metal lathe, and then on it you machine precise parts to improve it. And so your metal lathe gets better and better by you making the next version of itself using it, until pretty soon you've made your own metal lathe, starting with like a drill and a chisel or something. And the starting part is obviously the hardest, getting everything up and going. Anyway, so it's, but it's more of a kind of like thing that people do for a hobby, building their own metal lathe. Usually if you want to get into machining on a cheap, you buy a inexpensive one that's imported from abroad, and then you remanufacture parts of it to better tolerances so it improves. Yeah?
The metal lathe my uncle got was from a yard sale. It was an older 1950s model.
That's a good way to go. Yeah, the older ones are good.
Yeah, they take up a lot of electricity, but if you leave them running all day, it's less electricity than starting it.
Yeah, although it's a little harder to take your workpiece out while it's running. You gotta go quick with the chuck key. But yeah, startup is pretty intense on a lot of electric motors. And the bearings are great. There's very little friction. I guess you could chuck up like, I don't know, something with like flaps on it, and you probably burn up a lot of power.
My uncle just put a giant fan by it.
Yeah. Yeah. Oh yeah, so the kernel assembles itself, lifts itself up by its bootstraps. We'll go over this in great detail later. It'll be fun. That's next week, I think. And we might not get there like right away next week, so I want to actually show you how to write kernel modules a little bit, which I'm hoping to get you next time. So we have this demo here. Write a kernel module. Well, actually, we'll just grab the source code for one. That makes the keyboard LEDs blink, which is super fun. But it leaves them in a random state, kind of. Okay, any questions? Okay, cool.